You know? Merci. Well, it seems only yesterday I was standing here talking to you. But, I guess that was because it was only yesterday that I was here talking to you. Okay, so this is the last contribution that I'm going to make to the course. Today, I say we're somewhat moving towards lower energy, and Pierre has told you this morning about the physics of capture processes. What I'm going to talk about is the fusion of heavier objects, heavier ions at low energies. Okay, and I want to talk about this because we've been talking a lot about coupled channel effects, about nuclei coming in and there being composite objects with internal degrees of freedom which can be excited, and we've learned about coupled channels and BE2s and transition potentials and all these things. Okay. And fusion reactions where you bring ions together, as we'll discuss, below the Coulomb barrier. So that's one of your classic quantum mechanical tunneling situations where you have a Coulomb force, an attractive nuclear force, you get a barrier, and so you have a tunneling phenomenon. Okay? And most of what I want to do is to show you the experimental evidence that coupled channels effects of the sort we've been discussing. You know, nuclei have various sorts of excited states. Sometimes they're rotational, sometimes they're vibrational, sometimes it's a cluster-like projectile, and so the excited states are excited states of a pair or breakup configurations. I want to discuss in sort of general classical and quantum mechanical terms how those degrees of freedom affect the fusion of two ions at low energy. Okay, so that's the physics of this, and we'll see that these reactions are a rather sensitive indicator of such phenomena, and so in principle can be used to study such effects. But I'll say a few words at the end about breakup effects. The effects of breakup upon fusion are complicated, and it's still an open topic, and some people will say breakup increases fusion, some people will say breakup reduces fusion, and the experimental situation is certainly still not fully resolved. Okay, so here's my, we're going off the end again, is there? Any idea why we're losing about a fraction of this to the right? Because I think it may be a problem later on. Okay, well let's continue and see whether it becomes an issue. Okay, so there's my menu. I want to discuss the physics of what are called barrier passing models of heavy ion fusion reactions at relatively low energies. So we're talking about incident energies which are near to or well below the Coulomb barrier. Okay, so I want to talk about their description in simple quantum mechanical terms using potential models, and then I'll go on to discuss the importance of collective type coupled channels, okay, and how we can study those effects by a concept, for instance, called the distribution of barriers. Okay, and the idea that when you have coupled channels effects, your normal idea that there is a Coulomb barrier over which particles either are able to pass or tunnel through that barrier. We normally think that there is a Coulomb barrier, but we see that in the presence of coupled channels effects, in fact, the barrier splits, and you get several barriers. Okay, and that is reflected in a certain observable that you can calculate and a certain observable that you can measure if you can take very accurate data to study exactly which coupled channels are affecting the reaction rate. Okay, and I'll say a few words at the end about the possible roles of other degrees of freedom, such as breakup and transfer channels. Okay, transfer channels are turning out to be a very important channel, particularly when you've got neutron-rich nuclei, and it's probably fairly intuitively obvious that if you bring a nucleus in which is neutron-rich on one which is a regular nucleus, stable nucleus with the the comfortable numbers of neutrons and protons, if you like, then there'll be a tendency for this neutron excess on this side to want to flow onto the other nucleus to even things out somewhat. Okay, and that process is certainly seen in neutron-rich and weakly bound systems. Okay, so that's the menu. So let's start with discussion of what barrier passing models of fusion are. So this is it in a nutshell. We're talking about tunneling. Okay, so here's a picture with some fairly realistic potentials of what the interaction between an inert oxygen-16 nucleus and a samarium-154 nucleus might look like. Okay, and so there's an attractive nuclear well that we're now somewhat familiar with. There's a Coulomb repulsion, which is going up there, which we're also familiar with. Note this starts at 5 degrees. This obviously goes all the way down to the origin, but this is where the interesting stuff is. So the Coulomb interaction is repulsive, and you add those two together, and you'll get the red curve, and with what we would normally call the Coulomb barrier, with some height VB at some particular radius RB. Okay. The notations will change. This will become a big RB, I think, later on, but I hope it's fairly intuitive what that is. Okay. Now, there's another potential, of course, which isn't represented here yet. Because there's also a centrifugal barrier, of course. Okay. So depending on which orbital angular momentum this pair of nuclei come in at, then there'll be an L into L plus 1 over R squared like centrifugal term, which you'd also have to add in this to see what the potential the particles would feel in that particular partial wave are. Okay, so this is what it would look like in an S wave where there isn't a centrifugal barrier, but I think you can see already that if I came in with L is equal to 1 or L is equal to 20, then I'd have to add an additional repulsive potential onto this, and what it's going to do eventually is destroy this little hole there and kill off the barrier, and there'll be some point at which there's no longer a barrier and things will come in and get reflected, and there won't be any fusion, okay, because we simply won't see this attractive pocket in which the nuclei are able to capture. Okay, so barrier passing models of fusion are basically this. Okay, if you have enough energy such that you can start out here when the particles are separated and end in here at short distances, then you assume fusion has taken place, and either you've got there by going over the top of the barrier or you've got there by tunneling through the barrier, depending on what the incident energy of the particle is. Okay, so here's another picture. So here we are, we've got our standard description and any scattering, instant particle at some center of mass energy. It comes in with a certain momentum, with an orbital angular momentum, and this is the picture I've just shown you with a few more symbols on. I say, if these things get into, maybe you can just see this shaded area in here. The assumption of barrier passing models is if I get into this region on the inside of the barrier, then we say fusion has taken place, and we put another bean in the tin saying that's a fusion event, and we count up the beans to see what the cross section is. Okay, so we'll discuss how we take care of this fusion bit when we solve a differential equation later on, but it's already obvious. We've discussed many times the role of an imaginary potential. Okay, so one way of making sure that if stuff gets over the barrier then it stays in there and doesn't come out again is to put an imaginary potential at short distances, and as we've discussed, the imaginary potential at short distances would absorb the wave function in that region, and there'd be no opportunity then for it to bounce back, go through the barrier or over the barrier on the way back. Okay, so really what we're doing is just solving a Schrödinger equation for this potential energy as we've done before. Okay, there is now a barrier at some position RB. I told you it would turn to big RB. I didn't know it would change quite so quickly, but that's it. Okay, so there's a barrier at some position, and there's an outer barrier and an inner barrier. If I'm at an energy like this, clearly there's a distinct length over which we have to tunnel in order to get through if the incident energy comes in below the barrier height. Okay, and we will know, and I've gone on several times about saying the amount of stuff that comes in that goes out again is determined by the modulus squared of the S matrix element for scattering of this partial wave by this potential. Okay? And so the probability that this stuff is not coming out, hence it is either it's gone through the barrier or over the barrier, is determined by our old friend, once again, 1 minus mod S squared. Okay? So this is the probability that the stuff has flux has come in and it has not come back out again, and this is an alternative way of defining a fusion event as something that has happened in the inside. Okay? And this is our partial wave expansion. We've seen this all the way from the beginning of last week, and so what we need to do is sum up the contribution to the cross-section from scattering in each possible partial wave. There is a cross-section for each partial wave, and there's the usual weighting due to the number of substates for each value of L, and the pi over k squared is just the usual phase space counting factor. Okay, okay, so at the end of the day, that's what we need to calculate. And so if you have a potential, clearly you can calculate, you can solve the Schrodinger equation, work out this guy, and you have this cross section. Okay, so what's the interest in this? Well, as I say, very generally, astrophysics is always interested in the way nuclei interact at short distances. Okay, so at the lighter end of the spectrum, the fusion of light nuclei, carbon-12, 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 nitrogen, and stuff even lighter and stuff heavier, is important in understanding the reaction chains in astrophysical environments. Okay, clearly what I've got to say is also has some relevance to when you try and produce super heavy nuclei by synthesizing throwing two things together, calcium-48 and something else, to try and produce something which is massive. Okay. Okay, so the stars are just tend to indicate that what we think we're producing is some massive excited compound nucleus, and we're not interested in what this is. Okay, it's just that we're bringing this together, they come into close proximity. At that point you define a fusion event, and the understanding is that these have gone on to produce an excited compound nucleus. Okay, so there's our picture again. I've talked about 1 minus mod S squared. Another way of thinking about that quantity is to call it a transmission probability. Okay, so rather than an absorption probability in here, it's also called T of E. It's a transition probability through the barrier to get on the inside. Okay, and throughout the discussion, we're going to sort of assume, which is perfectly reasonable assumption, that it's really everything. It's what this barrier is doing that matters. Okay, so essentially everything is determined in terms of this transition probability about what the interaction is doing at the barrier radius. Okay, what is the potential here, which is determining how high the barrier is, and this is what's of key importance if you're going to do a realistic calculation. Okay, so barrier radii. So this figure is just really intended to show you where does this barrier normally occur. Okay, you bring two things together. There's going to be a barrier. At what point? How close do they have to be? Are they still 10 Fermis apart? Are they already very, very close together? At what point is the barrier? Okay, and this sort of diagram is intended to help you visualize this. Okay, the position of the barrier is normally such, if you bring two finite nuclei together, A and B, their densities are just starting to overlap in the tail. Okay, we don't have massive overlap. We haven't got massive perturbation of the ground states of these particles. They're coming together. They're just starting to get close to each other. So there's this balance between a strong Coulomb repulsion, and they're starting to feel, in competition with the Coulomb repulsion, the strong nuclear attraction and that. Okay, so what we take away from this is that we're going to be extremely sensitive in terms of where the barrier is and how high the barrier is to the nuclear binding, these densities, in other words. Okay, so the nuclear binding, how weakly bound the least bound nucleons are in this nucleus, will determine the tail of the nuclear density. Okay, We've seen that before during the course. We've looked at some Hartree-Fock densities for some neutron-rich things, and we see that the neutron density extends to larger distances. There's a neutron excess and whatever. Okay, so in this picture, if the density extends further, then the nuclear interaction starts to operate at a larger distance, and that'll certainly affect the height of the barrier. Okay, and so that's nuclear binding, if you like. Nuclear structure, really, this is talking about the same thing, but nuclear structure, I'm thinking rather more, if you've got a halo system, rather than just a nucleus with a neutron excess, which is sort of uniformly distributed around the edge. The next situation you might have is something like carbon-19 or something with a very weakly bound neutron, and then again, if there's a single particle which has an extended tail to the distribution, there'll be a component on this density extending to large distances. And so you might expect that you would see the effects of a neutron halo sitting on a nucleus in terms of what it's doing to the barrier and what it's doing to the fusion. Okay? But in the box is where things really get complicated, okay? Because once nuclear surfaces start to interact like that, then you're starting to excite degrees of freedom of the nucleus at the nuclear surface, vibrations or rotations or such like, okay? So we really should expect, based on this this sort of picture of where the important physics is taking place, that we must expect sensitivity and complications due to the reaction dynamics. And we've seen many nuclear reactions here in the last couple of weeks, and what we've seen is that mostly we're very sensitive to the potentials near the surface in order to be calculate those cross sections accurately. Okay, so we might expect then that if one of these nuclei was deformed, that's going to have a pretty big effect on this surface characteristic as well, etc. Okay, so this is another transparency that I've stolen from Koichi Hajino. So this is just summarizing where we've got to so far. Okay, and basically the problem is that I'm going to start with nuclei at large distances where they're isolated. They start out in their ground states. They've got some intrinsic states of their own. They might be vibrational nuclei or rotational nuclei, but I start them far apart, then coming in their ground states. Okay, and as they approach each other, interesting things happen, and they see this barrier, and I say they've either got to tunnel through or go over the top, and I say we're somewhere in the touching point. I say when we're here, the densities are just starting to feel each other. Once I get over here, then we're in a position where they really do start to touch. And once you go in here, you assume the fusion has taken place, and then you're getting big question marks everywhere. Okay, lots of complicated things can happen in there, but that's not on our agenda. Okay, we want to describe the path inward to this point. We want to start with the asymptotics, ground states and excited state properties of these, and try and examine how they get to this point, as I say, at which point we assume that they have fused, and then we draw a line under that and calculate the cross section. Okay, so we need a potential. So a standard way of calculating barriers, you know, we need the nuclear interaction. The Coulomb one is simple, Z1, Z2, E squared over R squared. That's not the problem. But we need a potential strong interaction between these two nuclei, say, which correctly describes the form of the potential at the surface. And so, again, we've discussed folding interactions, where you take wave functions for these systems, and because we've got the wave function for A modulus squared here, that means actually we've got a density of nucleus A, and we have a density of nucleus B, and some effective interaction. And this is a standard way of computing the nuclear interaction you need to compute the barrier, for instance. Okay? As I say, I don't think we've done this during the course, but if you do look at this integral, there are certain theorems that apply. Okay? For instance, when I've calculated this volume integral, this folded potential, it'll have a strength, which is usually called the volume integral, which is if I integrate that potential over all space, that'll give me a measure of how strong it is, okay? You know, the total oomph in this potential is given by integrating this potential over all volume, okay? And that'll be a number, and that'll be so many MeV, MeV Fermi cubed, and it'll be a measure of the strength of this interaction, okay? And I don't think we've done this for the folding potential so far in the course, but if I do this, then the oomph, the strength of the folded potential is the strength of the nucleon-nucleon force, which you put in this folding integral, times A1 times A2. Okay, that's a theorem. Okay, and so that's a check. If you're going to calculate a folding potential, and you have a wave function which is normalized, and you have an interaction, and you calculate this guy, once you've calculated it, if you integrate it up over all space, you must get the same number as integrating the volume integral of that and multiplying by the number of nucleons, for instance. Okay. More important to what I'm talking about at the moment here is that the extension, the mean squared radius of this potential is going to be the radius I started with, the radius of this guy, plus the mean square radius of the interaction between the pair. Okay. So what we're saying is that if you construct a potential from a folding model, you correctly build in this potential the range of this potential, the size of the two nuclei you started with, and the additional small contribution to the size due to the fact that the nucleons in the surface of that one, the nucleons in the surface of that one interact over an additional small distance. Okay, so that's the advert for folding models. They do that. Okay, if you've got densities for these guys, you build in the correct size of the objects into the interaction by working out such a guy. Okay, now say in a breakup context or a halo context, I was saying that the potential density at the surface may be different and the potential at the surface may be different. If there's a weakly bound system, a cluster system, or let's say this might be a nucleon, that might be carbon 18, we might be talking about carbon 19, or we might be talking about lithium 7, in which case this would be an alpha particle, and that would be a triton. Okay? But again, we've already seen this during the course. One way of calculating the interactions of such a composite, which has some internal wave function phi p, is to average the two-body interactions between these two guys over the range of the wave function. Okay? So again, if you doing such a calculation, there are theorems again that allow you to check your calculations or the calculations that are supposed to be coming out of these codes here. Okay, so you know, you should never believe a code, right? You should always think if this code is supposed to do something for you and calculate something, you should always think about ways in which you can check that those results are the correct results. Okay, and in particular, if you have a code that's supposed to be calculating this for you, then the volume integral of that guy, having calculated that, if I integrate it over all space, I should get the same value as integrating this one over all space and adding it to the integral over that one all space. Okay, and that's a mathematical identity which we can use to check things. Okay. More importantly, again, for this idea that extended densities will have an effect, is that if I do have a weakly bound guy here with a very extended wave function here, for instance, a halo state, then the mean squared radius of this interaction, well, there's a radius due to this interaction, there's a radius due to this interaction, and there's an additional piece due to the fact that this wave function is a finite size. Okay? And this bit here, if that wave function is a very extended object and very weakly bound, this can be quite a large number. Okay? And that means that the potential here will be much more extended if you're folding over an extended object. Okay? So these slides were really just in there because we haven't seen these identities before, but also to try and bring home the fact that we need to build in the structure of the nuclei that are taking part in order to get realistic descriptions of the potential that we're trying to deal with. Okay, so this is some calculations which were presented by Andrea Vitturi. This these are calculations of a barrier in a particular model if we take carbon isotopes interacting with lead-208. Okay? So what's happened here is that Hartree-Fock calculations of densities have been worked out, and then these folding potentials worked out, and then the barrier has been calculated depending on various neutron-rich carbon isotopes. Okay? And you can see here in this picture that the barrier calculated for carbon-12 plus lead looks like that. And then as you add more and more neutrons, and they go into obviously different single particle states, eventually ending up in carbon-19, where the last neutron goes into this S-wave halo state, you see this systematic reduction in the size of the barrier depending on how many neutrons you started to add. Okay? And in particular, there's two calculations here for carbon-19. One if the last neutron was in a D wave, and one if the last neutron was in an S wave. And you can see that the barrier is different. Okay? Small difference, but when you're doing fusion, some fraction of an MeV in the height of a barrier, because once you get below the barrier, it's very difficult to tunnel through the barrier. You can see that even the state of one nucleon would affect the shape and the height of the barrier to some extent. Okay? In other words, we might expect to see these effects due to what are called static properties. Okay? There's no dynamics here. Okay? All we're doing is calculating a folding potential as if carbon-19 would come in its ground state, remain in its ground state, and we're calculating the potential for the interaction of the carbon-19 ground state with the nucleus. Okay? There are other dynamical things that will happen. The carbon-19 can get excited. That's not in this picture. This is just the static picture based on the densities of the objects involved. Here, this is radius. This is the position of the barrier. Once you add the nuclear interaction, the Coulomb interaction, this is the bit of the potential which is really important for fusion. This is the barrier, and this is the position, and this is the radius here. Okay? 12 Fermis? Yeah?
Nuclear potential of fusion range is like a 2 or 3.
The nuclear-nuclear interaction. This is the interaction between carbon and lead-208.
Of course, the Coulomb interaction is common.
But this is quite a big nucleus. Right? Do you know how many Fermis the radius of lead-208?
Yeah, of course, R0 times A to the...
Okay, so what's that?
Yeah, okay. Yes.
Okay, so
So 200.
lead has a size, lead has a size, and carbon has a size. Okay, and then you bring those two together and ask at what radii do they start to, their densities just start to overlap. And these are calculations of that within a model. Okay, and if it's carbon-12, that distance is smaller. Carbon-12 is a small compact object coming towards lead-208. Okay, as you add more neutrons, the carbon isotopes become bigger. They swell up, like us. Too much lunch, we swell up. Okay, and so they start to interact at larger distances. So the barrier is moving out and moving down. Okay, and that would change the cross section. Okay, if this would say that if I do a reaction at 55 MeV center of mass, yeah, then I'd already be below the barrier for carbon-12, but I'd be above the barrier for carbon-19. So one reaction would go very fast and one reaction would go very slow to produce fusion. Is that right? Yeah. Was there a question there?
I guess just so it's the distance between the center of mass of the two nuclei.
Yeah, I'm sorry. If that wasn't clear, then I apologise. Okay, I mean what we're talking about here is the barrier. Okay, so this is, as you know, we've been discussing these pictures, and this is the barrier. So we're looking at this bit here in terms of the centre of mass distance between the two objects. Okay, so those are, as I say, those are static properties. Okay, so the challenges. Okay, what are we going to have to worry about when we do this sort of analysis? Okay, so that's the sort of bottom line. That's what I've been trying to warm you up to. Okay, that we expect a complex interplay between these static effects, that the ground state densities look different, and surface effects, dynamical effects, which we haven't really talked about yet. Okay, and far below the barrier for normally bound nuclei. I mean, if you go far below the barrier, you don't have much energy, okay? And in order to make direct reactions happen, you have to have enough energy coming in to excite the states, okay? And as you go to lower energy, reaction channels turn off. Okay? If you've got a state here at 3 MeV and you come in with 2 MeV, then you haven't got enough energy to excite it. Okay? So as you go below the barrier, some reaction channels that might be important at the barrier will gradually turn off, and so the coupled channels problem that you would need to solve, which are the important coupled channels, will change as the energy reduces and the energy available goes down. Okay, so as I said, fusion is expected to be a severe test of models of nuclear structure and our treatments of these dynamical effects because of the surface sensitivity. On the positive side, there's been a lot of effort in certainly these laboratories and others, but at the Australian National University at Canberra, at Sao Paulo, and in Lignaro, I guess, have been the major centres where they've been trying to push the error bars and such data down in order to make really quantitative discussions of these things. Okay? And last of all, these weakly bound systems are different to some extent. Okay? As we've seen, there are going to possibly large static effects for halo systems, but when they're weakly bound, we also get breakup as an important channel. Okay? And that channel is potentially also very, very interesting. Okay, so I'm showing this data as an indication that channel coupling is probably going to be an important property in these systems. Okay? So on the left-hand side, there are 3 sets of experimental data. This is a fusion cross-section, let's be clear. Okay, this is a fusion cross-section in millibarns. This is the energy relative to the height of the barrier. Okay, so if you see one, so that you can plot these 3 data sets on the same plot, this is what happens if the energy is equal to the energy of the calculated barrier. This is below the barrier by 10%. This is above the barrier by 10%. Okay, so this is for oxygen on samarium isotopes, and it is known that as you go from samarium 144 to 48 to 54, those nuclei become increasingly deformed. Okay? And so there will be states at low energy. As you go up in this direction and increase the deformation, there will be low-lying excited states corresponding to excitations of the deformed system. Okay? And these are the data. Okay? The arrow goes in this direction for the nuclei, and the arrow goes in that direction for the data. Okay? So samarium 144, the data start in this place, and then they come down here. Okay? Look at the scale. Okay? So when you're at the barrier, the cross-section is about 100 millibarns according to this plot. And then when you're 10% below the barrier, you're down at about 3 orders of magnitude or so. Okay? So these are sub-Coulomb barrier. These cross-sections rely on you tunneling through the barrier. And we can see that the measured cross-section for these 3 are characteristically different. I say the masses are changing, but I say there's relatively small changes in the mass compared to a mass of 150, and the changes in the data are huge and move in this direction, increasing the cross-section with the deformation of the particle. Okay? So it looks as if deformation is playing an important role here in the interpretation, and that deformation is enhancing the fusion cross-section at low energies in this plot. Okay? On this side, it's the same axis, the reactions are different. Okay? Now, on this picture, there are reactions of nickel isotopes with nickel isotopes, and two of these are symmetric, so 64 on 64 and 58 on 58. Okay? And in the one in the middle, it's asymmetric, so it's got 64 and 58. Okay? And so there are circles and triangles, and the circles and triangles both lie on top of each other here, actually. Okay? I don't know if you can see them both, but on that first curve that drops faster are these two, and that guy, which is asymmetric, is these data points where I put the green box sitting over there. Okay? So going in this direction here, starting here and going out in this direction, what we've got is an increased neutron-rich nucleus on one side of the pair. Okay? So looking at that, you might expect that maybe this enhancement here is due to the effect of these things coming together and the neutrons wishing to equilibrate and pass from one nucleus to the other in the collision. Because where it's symmetric, you see no difference in going from 64, 64 to 58, 58. Okay? So this perhaps is an indication that transfer of neutrons from one to the other also has the effect of enhancing the fusion at low energies below the barrier. Okay, so I think we've got some formulae coming up. Okay, so let's look at this curve, only this curve over here. There's that dashed curve over there, hope you can see it. It falls too fast compared to any of the data. Okay? None of these data agree with that dashed line, and that dashed line is what you get if you make a sensible choice of the potential so that you reproduce this cross-section up here near the barrier and above the barrier. You've got to fix the potential somewhere, so you get the barrier right by fixing this data, and then you carry on to lower energies and the data, and the cross-section falls too fast. Okay? And that is assuming that the two nuclei are inert. It's spherical oxygen-16, a potential with a spherical samarium isotope, and it falls some way away from the samarium-144 data and a long way away from the samarium-154 data. Okay? So we get one, without putting in excited state degrees of freedom, one continually gets this sort of behavior where the fusion cross-section drops too quickly with energy below the barrier. Okay? And this plot shows that you can't fix that by simply making the potential a little bit shallower or something to move the barrier around so you get more transmission at the lower energies. So essentially that's that plot again. If you change the potential depth to just try and lower the barrier a little bit, you move it up, but you can't reproduce this. So there's some other physics going on than simply spherical nuclei tunneling through a single barrier due to the Coulomb and Strong interaction. Okay? Okay, so let's talk about some formulae and some simple models. Okay, so this is summarizing what we said earlier on. This is one way of calculating within a potential model what the fusion cross-section is. Okay, you need a potential, you put it in the differential equation, you work out the S matrix for that partial wave, you work out these transmission probabilities or absorption probabilities, whatever you want to call them, and then you work out the cross-section by adding up the contributions from each partial wave. Okay, and we should all be able to do this now. Okay, we've had lots of experience of solving differential equations this week. Okay. Okay, so let's just mention how a calculation is done. I think I mentioned one of these already. Okay, so you need to numerically solve this second order differential equation, having chosen your potential and your partial wave. Okay, and so that's just a radial equation to solve. We can all solve second order radial equations. Numerov method was mentioned this morning. You pick up your favorite algorithm and you integrate this differential equation. Okay, and we need some boundary conditions to do that. Okay, second order differential equation, there is no unique solution without applying some boundary conditions which constrain the solution to the physics. Okay? So there are two things that are usually done in these passing models. You remember what we said is if the particles get in here to short distances, you say fusion has taken place, and that's it. Okay? So there's two ways that are traditionally used to do that, okay, as a boundary condition of this equation. One is that you require that these equations, when you get into the interior region, you require that those waves have incoming wave boundary conditions only at some radius. So you choose a radius inside the nucleus here, different from these. So let's call it R inner. Okay? And at R inner, the wave function you require essentially only has incoming waves. Okay? Of course, if it's in partial wave L, the incoming waves look like our H minus functions or whatever, but basically we're saying there's only an incoming wave there, so there's no reflection and no chance of anything going back out. Okay? So that's one way of applying the boundary condition. The other way of sorting out the absorption in this region is, as I said before, you just add a strong imaginary part to the potential at short distances, and then anything that does come in here, the wave function decays away exponentially and doesn't get back out. And solving the differential equation with either of these gives this the same outcome for the S matrix and for the fusion cross section.
If you don't use one of these methods, if you use standard S matrix, what happens?
Well, you still need a boundary condition. I mean, if you're above the barrier and you solve with the normal method, and you don't have an absorptive potential or other, then I'm going to get total reflection, right?
But if the is V complex or real?
V would normally be real, yeah. V will be with sufficiently low energy that there are very few channels open, and those channels that you think are important, you would like to put them in explicitly as a coupled channel rather than hide them in an absorption. Okay, and so that's the logic of this. The V's I've been talking about are real V's, okay, and the absorption when you put it in is to do a particular task and say there's something complicated happening at short distances and I don't want to consider that. Let's just put it into absorption, and otherwise this potential is real. Okay, so there's no other loss of flux due to excited states. And what we would want to do is, if I think there is a strong and important excited state with a rotational nature or vibrational nature, let's put it in a coupled channel and deal with that in an explicit fashion rather than trying to mop it up with an imaginary potential. Okay, so the first classical, what do we expect? Okay, what do we expect to be the result of this? Okay, so this is that picture I hinted at the start. Okay, I don't know if you can read this, but we had a barrier, which I said was, of course, probably what the barrier looked like for L is equal to 0, because I then don't have a centrifugal barrier. Okay, so this one's supposed to be L is equal to 0, and then you add on the repulsive centrifugal barrier for, in this case, it's nickel plus nickel, and this says 30 H bar. Okay, so I'm adding in on the centrifugal barrier for 30 units of angular momentum in this case. And they're very heavy objects, okay, so they rapidly pick up angular momentum as you bring them in with even modest energy. And that one, 60 H bar, okay? So this is to show you that when we're in a given partial wave, the potential that is seen because of the centrifugal barrier will change. Okay, it'll be slightly different for each partial wave. The V isn't changing, but the overall potential with the centrifugal barrier is changing. Okay, so you can see that if this is where the incident energy was, say I came in at this energy here, whatever it is, Okay, I guess it's 108 MeV or something, if where I've placed that red line. You can see that L is equal to 0. In the L is equal to 0 state, this will perfectly happily get over the barrier, go into the inside and fuse. Okay. Similarly, up to 30 H bar, it still goes over the top of the barrier and it'll fuse. Okay. But by the time these two are in a partial wave where L is equal to 60, the waves coming in are going to hit this barrier here and go back out, and fusion will be cut off. Okay. So what you can see from this diagram is that if you throw things together at low energies, some angular momenta, there's going to be a barrier which it can go over the top of. Some angular momenta will be right just near the barrier. A few angular momenta will be close to the barrier but just below and require tunneling. And then as the angular momentum goes up, the barrier becomes too wide or non-existent, and the fusion will cut off, and the stuff would simply be reflected and not get into my interior region where we say fusion is taking place. Okay? In other words, the transition probability classically is going to look something like this. Okay? There's going to be, the transition probability is going to be 1 classically as long as I'm above the barrier, and so it will be, and then at some L max where it's put in our sort of semi-classical rules, the wave number times the barrier radius. When the L max is of order k times the barrier radius, suddenly this guy will hit this point. Classically, it won't be able to get over the barrier anymore, and this transmission coefficient will go to 0. Okay? And so that's the classical expectation, that step function there. And we know that all quantum mechanics does to classical predictions is it smooths them off a bit. And so in the quantum mechanical case, there'll be a little bit of reflection even if I'm above the barrier and close to it, and there'll be a little bit of tunneling on the other side, and we'll smooth it off and look like that. Okay? But you can see if the transmission coefficient is constant up to some L max, then when I compute the cross-section, our fusion cross-section, reaction cross-section, call it what you like, by doing this sum, then T is 1 up to some L max, so I have to sum this guy up to L max, and that gives me this guy here. Okay? And of course, K times RB is L max, and so that says, gives us our nice result that we might have expected, that in a sort of simple classical picture, the cross-section for this thing coming out and fusing completely is something like pi times the barrier radius squared. Okay, so that's a base mark for how big the cross-sections are likely to be. Okay, well, I'm not going to talk about this one, but say if I'm going to put it in here. There's a very famous paper by Wang, which was sort of rather influential at the start of this work, and my summary of this is that you've got a barrier which is some rather complicated shape in general. Okay, it looks more like Coulomb tail on this side and the nuclear interaction, and then so it's not a symmetric barrier, it's an asymmetric barrier. But if you assume the barrier here near the top is quadratic, it's just a parabolic barrier, then you can do a lot of the quantum mechanics analytically and get some analytical results out of that. Okay, but this isn't mainstream to what I want to talk about. But if you enjoy the formulae and you enjoy the quantum mechanics, then I say what this is really about is working out the transmission coefficient through a parabolic barrier. And so it allows you to get a more sophisticated analytic answer if you've got energies which are near the barrier, at the top of the barrier where it does look rather parabolic. Okay, so let me do something a bit more complicated. Okay? All right, so how do we make a link then between these transmission coefficients and the cross-section and things that are measured? Okay, well, this I think you've all done quantum mechanical tunneling through a barrier. Okay, now I don't expect you to derive this formula, but you will know that you can obtain the tunneling probability by doing integrals of stuff. This is an effective wave number essentially between the inner and outer barriers on this thing. Okay, so I want you to take this one as given. Okay, so what I'm saying is there's a perfectly respectable quantum mechanical formula using WKB-like ideas that allow you to work out the tunneling probability through the barrier based on what the barrier is, the energy, the angular momentum, and such like. Okay? Okay, and let's remind ourselves that really it's what's happening at the barrier that's all important. Okay, it's what's happening at that point which is all important. Okay, now you'll note that this is the transmission coefficient for a given value L. Okay, and L appears in here through this factor here. All right. Now you will also see then that if I take this term and I assume actually the value of R that really matters in here, R is a variable and R is an integration variable. Okay, so that sort of makes it more complicated. Okay, but if we say, well, actually the value of R that really matters is the value of R at the barrier, and so I say this thing is equal to L over L times L plus 1 over the barrier radius squared, okay, where R of E is the radius of the barrier, then this term becomes a constant, okay, worked out at the barrier position. Okay, and you see if I do that, then this general term for an arbitrary L I can think of as the same expression calculated with no term there, but lumping that contribution for the fixed R into the energy to give some modified energy. Okay? So if I can argue that this centrifugal term is dominated by what happens at the barrier, then that expression there I can rewrite as this transmission coefficient I would get if L is equal to 0, but replacing E by E dashed, where E dashed is this thing containing this contribution. Okay? So that approximation, the transmission coefficient at any value of L is the same thing as the transmission coefficient for L is equal to 0 calculated at approximate value of the energy. Okay? Now this little derivation down here is rather key to what's going to go on next. Okay? So I really encourage you, if you want to know what's going on in detail, to work through this bit of algebra yourself, and I'll point you to what's going on here. Okay, so here we are. So let's start. So we're going to use this guy that we've just been discussing here. Okay, so let's write down the cross section for the fusion cross section of E. As we've seen, it's a sum over contributions from different partial waves. Okay, and let's assume that there are contributions from a number of partial waves, several partial waves. We've just seen nickel on nickel, where there may be 30, 40, 50 partial waves all contributing. And so let's assume I can replace that sum by an integral over L rather than a sum over L. Okay, there are many L's, so let's just treat it as a continuous function of the L index. Okay, I think people are probably happy with that. Yeah. Okay, now, as we've seen, sigma of L is what? Sigma of L is this guy down here, right? The contribution from a given partial wave at a given energy, what we've seen, is pi over k squared 2L plus 1 times the transmission coefficient for energy E. But what we've just shown up here is that to a reasonable approximation, TL of E is given by T0 at some adjusted energy E prime. Okay? So what I can now do, seeing as I have a relationship between, this is E dashed, and that is L. Okay? So what I want to do is now change the variable in this integration, and instead of integrating over L, I can change the variable to E dashed. Okay? Perhaps you can see what it's going to be. Okay? If I take a d E dashed, it's going to involve, what's this thing here? L squared plus L. You agree? That bracket is L squared plus L. Okay? So I take an infinitesimal element of dE dashed. This is a constant, so dE dashed will be minus 2L plus 1 h bar squared over 2 mu that. Okay? So there's a little bit of algebra involving a change of variable from dL to dE dashed, and if you do that, then you can convince yourself really rather straightforwardly that this quantity, the sigma times the fusion cross-section as a function of energy, is what we had before. In the classical model, pi times the barrier radius squared, and that is multiplied by an integral from 0 to e of this transmission coefficient here. Okay. Now, so if you spend 5 minutes just doing this integral transformation, you'll find that, and then everything else that follows will be perfectly clear. Okay. Otherwise, if you don't want to do that, then you'll have to believe me that I have done that correctly. Okay. Okay, so on the next slide, I want to use this and see what we might expect in our semi-classical, our classical description, or in a quantum mechanical description. Okay, remember this. I hope I've written it on the next slide as well. Okay, there it is, that guy there. Okay, so this is where the discussion of distribution of barriers comes in. Okay, what does that quantity look like? Sigma times the energy if we have our classical transmission coefficient that we talked about earlier. Okay, well, our classical transmission coefficient, if you remember, now what we're talking about now is what is the transmission over the barrier as a function of energy. Okay, and hopefully we're aware that if I come in with an energy below the barrier, there is no transmission, so T is 0. And at some point I'll hit the barrier, and once I go above the barrier in energy, the classical transmission coefficient jumps up to 1. Okay? And so if I compute this integral here, if I work out this quantity as a function of energy, then putting the fact that the radius of interest is the barrier radius, you should be able to see rather directly if this upper limit E is less than the barrier, I'm going to get nothing. And so the value of this is 0 for energies less than VB. And if I am above the barrier, then I get no contribution between 0 and the barrier height, but then I get a linearly increasing contribution as the energy for the piece of the energy which is above the barrier. Okay? In other words, E times sigma V of E looks like this thing, our classical cross-section times E minus VB. Okay? So this object is 0, and then it's the barrier, it rises linearly. Okay? So if I take this quantity and differentiate it once, I guess we could have the plot. Let's do a lum. Okay, I should have put the step in, I guess, but I didn't. Okay, so what we've just been discussing is this quantity E times sigma of E, and we've if I differentiate it, let's draw it first. Let's draw that guy. Okay, so according to that definition there, classical. Okay, according to that, as a function of E, there is the barrier. Okay, so this thing comes along 0, so we can see it, and then it rises linearly like that. Okay, E minus VB. Okay, so if I work out the derivative of this in a different color, you can tell me. If I differentiate this quantity, what do I get? What's it here? Hope it's 0. And what happens when I get there? Constant? Jumps. So it'll jump up and then become some constant. Okay? Good. I've still got one color. Okay, so let's now work out d2 by dE squared. What does that guy look like? Come along here. What's the derivative here? And then it goes to 0 again. Okay, so this is something looking like a delta function. Okay, but a spike. In other words, what this is saying is classically, if I'm coming in and I've got a barrier, a simple barrier like this, classically, then what I expect this quantity to do is that it tells me where that barrier is, because this quantity is nothing. It says I've got a single barrier at this point and then nothing more. Okay, so I can look at that quantity and it tells me about the position of the barrier or barriers if there would happen to be more than one. Okay, is that all right? Okay, so this quantity, this analysis, oops, beg your pardon, getting to that point on the previous slide is rather important because, as I say, it allows us to interpret this guy. Okay, and so that's classical. Oh, the answer was on the slide all the time. No wonder you got it. And it's even in red. Same as over there. Okay, so what we'd expect quantum mechanically, of course, is everything gets smeared out a little bit. And when you do these integrals, there'll be a little bit of smearing, and we would expect this guy to then become some sort of Gaussian, some sort of bump around the barrier position, but really rather well localized if these are spherical nuclei with a well-determined barrier. Okay, and that's an example where a certain set of experimental data for calcium-40 on calcium-40. Now these are prime doubly closed shell magic nuclei, good spherical nuclei. Okay, so fusion cross-sections have been measured, accurate enough so you can differentiate them twice, and that's what this quantity looks like as a function of energy. Okay, and you can see directly experimentally that there is a barrier between calcium-40 and calcium-40, and it sits at about 52, 53 MeV high. Okay, so this is a way of experimentally directly observing properties of the barrier. Okay, so it's rather nice. Okay, it's not guessing stuff. If you've got this data, you know that whatever potential model you start with, or your final calculation must reproduce this barrier, at this point, this barrier of that height. Okay, so let's go on. Okay, so let's think about this coupled channel effect now. Okay, so I put this in again just so that if you still haven't got coupled channels, then I wanted to write very explicitly the equations down. Okay, but I say I'm not going to go through this particularly, but what I want is to see what the effect on this calculation we had over here might be, this classical calculation, if instead of these being spherical inert nucleus, I come in and there is a single excited state that can be excited, and I've represented that here. Okay, so think about a model problem where two nuclei come in, they're in some initial state E1, state 1 with some energy, and let's assume there is another state in the problem where we can get an excitation to another state. It might be a rotational state in the projectile, it might be a rotational state in the target nucleus, it might be something else. Okay, but let's assume there is an excitation that is possible. Okay, and the way that I've drawn this is that there is an internal Hamiltonian for this projectile, which depends on some internal coordinates. So that's an internal intrinsic Hamiltonian for this piece. And as I bring these two together, there is an interaction F, which couples the center of mass motion R to the internal degrees of freedom of this. And so as I bring these two together, this Hamiltonian allows that guy to be excited. Okay? And let's assume there's a single state it can be excited to, which is state 2. Okay, so that means that this is the Schrödinger equation we would need to solve with this Hamiltonian, and we know that the solution looks like a bit where waves scatter from the object in state 1, plus another bit involving relative motion where the object is in state 2. Okay, and the incident waves are in this guy. Okay, as I've drawn it, this is the channel in which the particles come together. So in this wave there would be incoming waves in channel 1, and there would only be outgoing waves in this state phi 2, because that one is the one that's coupled to. Okay, so we know that with this sort of coupled equation, I can then act with state 1 on the left hand side and get some stuff, and act with state 2 on the left hand side and get some stuff, and we end up with a pair of coupled equations here where we've got some F's which tell us how this interaction behaves in channel 1 and channel 2, but more importantly, this thing here is responsible for coupling channel 2 back to channel 1 and for coupling channel 1 to channel 2 in the first place. Okay, so I just want to remind you, this is how you would model a pair of coupled equations where you've got a two-state problem such as this. Okay, and I want to make it even simpler on the next slide. Okay, so in the context of what we're doing here, if I had a model problem like that with two channels, such as this, it would mean I've got instant waves coming in on channel 1. So there'll be waves coming in and waves reflected, and some of the waves will be transmitted and will fuse. Okay, channel 1 can couple to channel 2, and so in this process there'll also be some excitation, and so there'll be some waves coming in, fewer of them. There'll be some flux near the barrier in channel 2 due to the excitation, and some of that can get, I've drawn it further down because there's some excitation energy involved, so the energy available in the centre of mass would be slightly less in that channel, and some of this flux which is near the barrier in channel 2 due to the excitation will be reflected and some transmitted. Okay, so in other words, the fusion, we would expect some of the fusion to happen due to particles in channel 1 and some of the fusion to take place as opposed to due to particles that are being excited to channel 2 and are going through with a reduced energy. Okay, so to look at this algebraically, well, there's a pair of coupled equations there. Okay, and I've assumed here that let's make these two states degenerate. So instead of having on the previous slide different energies here, okay, and let's assume these states are degenerate, and let's assume, so those terms go away. Let's assume that these interactions are the same in channel 1 and channel 2, so let's make those two the same, and let's assume that the coupling going one way and the coupling going back is identical in there. Okay, and if you do, you get a very simple pair of coupled equations for state phi 1 and phi 2, which essentially look exactly the same, except that this is 1, that's 2, this F coupling 2 to 1, and this is F coupling 1 back to 2. Okay. Now the point about this pair of coupled equations is that you don't need to be able to solve coupled equations to solve these, because if you add these two equations together, I get an uncoupled equation, and if I subtract these two equations from each other, I get another uncoupled equation. Okay, so there's a trick. Adding and subtracting these guys allows you to decouple this pair of coupled equations and solve for two uncoupled equations instead of solving a coupled equation set. Okay, so that's what you get. If you add as you can probably see, there's an F there, and if I add the equations, I'm going to get something with a plus F, and if I subtract the equations, I'm going to get something with a minus F. Okay, so as I say, if you add and subtract the two equations and put an appropriate normalization so that you preserve the flux involved in those two equations, then you find you get two equations which are decoupled. Okay, but the important thing is that in one of the equations, which describes half the incident flux coming in, it sees a barrier where the barrier is V plus F, and in the other half of the flux coming in, due to the other channel, it sees a barrier which is V minus F. Okay, so it doesn't matter whether F, the coupling, is attractive, plus or minus, you will always get a splitting of two barriers, and coupling to this channel, no energy is involved. Okay, it's degenerate, but I couple to this other channel, and in the process of doing that, if there's an interaction with that coupling, I'm going to get a problem which effectively sees two barriers, where one is higher, and for that part of the flux, the fusion is going to be reduced. But more importantly, some of the flux is going to see a lower barrier, and it'll like that, and the cross section will go up. Okay, so what we see from this is that from this simple example is that we expect a coupling to another channel to produce a barrier which is reduced for part of the flux, and this will enhance the fusion cross section. Okay, so there's a picture there, a schematic. There's my barrier, and say one is going to go up and one is going to go down. Okay, and if things are coupled in the way that I've done it there, then I say you add and subtract these equations, and there's half the flux in the channel with the lowered barrier and half the flux in the channel with the higher barrier. Okay, so when I work out the transmission coefficient now, I say there are two barriers. Okay, so if I work out the transmission coefficient now classically, I go along, and as soon as I hit the lower barrier, half of the flux can get over it. So there'll be a transmission coefficient of 1 for half the flux, and so half the stuff can get through. Okay? And then there'll be nothing else happen until I hit the second barrier, and then the other half of the stuff can get over, and it'll jump up like that. Okay? So what we expect now for the transmission coefficient in a coupled channels problem is a step up like this. Okay? And if there are 3 channels, we'll have 3 steps, and if there are 4 channels, we're likely to have 4 steps. Okay, so that's what I'm trying to draw. And of course, quantum mechanics will smooth these things out, smooth off the rough edges. Okay, rather like a Calvados at the end of the day, you smooth off the rough edges of the day and produce something smoother. Okay, but we can now use this in our discussion over here and ask what would the barrier distribution look like, because I've got a transmission coefficient. We had that integral over transmission coefficients that told us how to calculate the fusion cross-section, and then we can differentiate it. Okay, and perhaps no surprise, so if our transmission coefficient looks like that rather than what we had before, when you differentiate this thing with 2 steps, you'll find you get 2 delta functions. One positioned at the position of the lower barrier, and one positioned at the position of the upper barrier. Okay? So if I can calculate if I can measure the cross sections accurately enough so that I can work out this quantity, I should get a visual representation of what's going on, looking something like that, and seeing a distribution of barriers like that is telling me there's a strongly coupled channel which is affecting the low energy fusion. Okay, as I said in the box here, I've divided it up. I assumed the 2 channels were degenerate, so there was half the flux in one and half the flux in the other. If you put the excitation back in, then the flux is not equally divided, and one will carry more, so perhaps this one will be smaller and that bump will be bigger, or vice versa. Okay, but in more complicated cases, clearly you have to diagonalize whatever the matrix is that gives you the coupling of those channels in the appropriate way. Okay, so I've seen this before, so we don't have to dwell any time on that. That's the issue. Okay, so we're interested in this case over here, really, at the moment. I'm not talking about transfer of particles. We're talking about exciting perhaps a low energy 2+ state, which represents the fact that these guys are deformed. That would be a natural channel to couple to, and perhaps this increase in cross-section with deformation is just a manifestation of that lowering of the barrier we've been talking about, associating with a strongly coupled channel in such a case. Okay, so here's some pictures and measurements. Okay, and some of them will show 2 bumps. So down here at samarium 144, this is the density, this is the distribution of barriers for this system. Oxygen 16 on samarium 144, and there's distinctly 2 bumps. This is nickel 58 on nickel 60, and it looks as if there's certainly 2 bumps going on there. Okay, but what we're not getting is something that approximates a single delta function, indicating that there's a single barrier at work in this problem. Okay, and so that's the calcium 40 again. That's a spherical example, and you can see all these other cases have either tails or different shapes or interesting things going on, indicating that coupling to either vibrational, rotational, other sorts of excitations are generic in these systems. Okay, what's going on? You have to look at the channels that are available and think about these couplings in order to get quantitative descriptions of these observables. Okay. So I think pretty much this is the story that I want to give you, okay? That what I'm trying to do is use some simple classical ideas and the formulae for the fusion cross-section to bring out these features here of what the transmission coefficient is doing. We know how to calculate the transmission coefficient by solving radial differential equations and trying to see how you can then interrogate data using these ideas. Okay, so the homeworks. There's 2 homeworks if you want to do them. Okay, and so I'm going to ask you to use a bit of code, say if you wish, to look at some of these things. And so one example, it's asking you to do a calculation involving oxygen 16 plus samarium 144. this is thought to be a vibrational nucleus, okay? And so what we're talking about is what's happening to the barrier due to the fact that I've got a nucleus here as a target, which is a vibrational character. And so you can generate a potential, turn off this vibrational cupping, do the calculation, see what you get over here, and see what you get down here. Okay? And if there's no coupling, as we say, what we would expect to get a single peak somewhere in some place, saying I've got a single barrier at some height. Okay? We can then put in the coupling, the vibrational excitation of this guy, do the calculation again, and look at what has happened to the cross-section. Have we got enhancement to the fusion cross-section at low energies? And what has happened to this distribution of barriers? Okay? And you should get something like one of these. These calculations are more sophisticated than the one I'm proposing here, but we can certainly put in, easily do a calculation with an octopole phonon here, coupling the 0 plus to the 3 minus state, which is a low-lying state in this system. Okay, so that's one thing we can do. And I hope, based on what I've said, you've got an idea what these observables here are telling us about the physics, the barriers, the potentials, and the coupled channels. Okay. And the other thing we can do is the rotational example. So, as we said, this is the more deformed end of these guys, right? There's that one over there, samarium 154. So it's that data that sits out there on the edge, the most deformed one. And I say it's rather easy to set up a calculation using this code CC full, which is there compiled up for you, to do a calculation where you include excitation of the rotational band in samarium 154. And I think this is the calculation you will get if you assume it's spherical. And once you do this coupled channels calculation, you should get something which is a considerable enhancement out here in the low energy fusion tail. Okay, and there's a characteristic form for the distribution of barriers also. Okay, so this diagram is actually showing you the curve of what you expect if the system is spherical, and it doesn't look like that. Okay, so there's excitations going on, and one way of modeling this system is as a rotational excitation of this deformed object. Okay, so I think I've probably spent enough time. Let me just spend, with two transparencies, just saying a couple of words about weak binding. Okay, so what we've done there is rather well-bound nuclei, intrinsic degrees of freedom of the traditional kind, vibrational excitation, taking into account the fact that these are not billiard balls, but they're really dynamical objects which feel the nuclear interaction and can get excited. Okay. Now treating breakup is a whole different matter, really. I say, when a system coming in and it's loosely bound, then you would expect that it breaks up, and this adds the additional complication that perhaps sometimes it does break up, but it breaks up near this target nucleus, and both bits that are already separated are close enough to get captured on here and produce a completely fused object. Okay, and this is sort of complete fusion, which is what we've assumed we've been calculating up to now. Okay, but you would also think perhaps that it's much more likely now for a weakly bound object that this thing comes up, it dissociates, and one bit is already sufficiently far away that it doesn't get captured, and the other one does, and so we got a fragment, and then we've got an incomplete fusion event where only part of the projectile has been captured. Okay, so this is rather intrinsically more complicated to calculate, and it's tough to calculate the effect of breakup on fusion. Okay, we know lots of weakly bound stuff. So there's some stable stuff like these cluster states which are weakly bound, and so those are easily broken up. So you can certainly test these ideas of breakup on these weakly bound systems like beryllium-9, lithium-6 and lithium-7. Okay. Of course, we've also got these unstable guys, these exotic neutron-rich guys, which are more weakly bound, but of course these are hard to produce with intensities to do very precise and accurate experiments. Okay, but people are trying. People are trying to learn what the implications of this weak binding are on the fusion process. Okay, I say it's not obvious what is going to go on. Okay, there's two effects. The static one I talked about at the start, Okay? If we really do have weakly bound particles, then we expect the densities go out to larger distances. You feel the nuclear interaction faster, so you might expect the barrier to be lower, and that might lead you to expect that you get a larger sub-barrier fusion. We've seen that if we couple in any channel, we get a split of barriers. Okay, so you might expect that when you dynamically excite this to breakup states, that's just another excited state. Then we might expect a larger fusion cross-section from that. Okay. However, as we said, breakup by definition moves the stuff apart, and if you're coming in and some of your beam is dissociating, then you might think that that's a big leverage, that less of the particles get to the scene where you actually want to fuse them completely anyway. So this goes in the other direction, and also we've got this thing down here. Okay, once you're really neutron rich, you've got large positive Q values for neutrons wanting to go over. So a real competitive channel is not breakup, but this thing gets close enough that the neutrons really want to spill over into the more symmetric system from this very asymmetric system. So these are all issues that need to be treated, and it's no mean feat to do these experiments with the neutron rich as well, of course, because we don't yet have very strong beams, but I guess Spiral 2 will take us some leap in that direction when it arrives. Okay, so the court is out, okay, and to what is happening. So I'm just going to flash a couple of slides of data. These are data showing fusion cross-sections for beryllium 9, 10 and 11. Okay, so 9 is weakly bound, as we just said. 10 is a more regular nucleus. Beryllium 11 is a halo. And within the statistics of those experiments, it's very difficult to see that anything very dramatic is happening on the fusion cross-section, whether it's weakly bound or not in this light system. Okay, so that gives us no great perception that the halo and the weakly bind is increasing the fusion cross-section at low energies, for instance. There's this piece of data for helium-6 and helium-4. Okay, so Antonio talked about the elastic scattering of these halo states in his examples, and you can certainly see in the elastic scattering, so this is ratio to Rutherford for the scattering of the alpha particle and helium-6 from zinc, and you can certainly see that the extra 2 neutrons make a considerable difference to the elastic scattering. Okay, so that must mean the potential energy is significantly different, and there have been measurements of helium-4 and helium-6 fusion on uranium-238, and those also look very different. Okay, so it does look as certainly is that there's some interesting physics, and the fusion cross-section is well aware of those extra 2 neutrons that are sitting in the helium-6. Okay, but I say that the careful analysis of that data is summarized on this transparency, where by making more exclusive measurements where the helium-6 came in, and not only did they look at helium-6 having disappeared, if you like, but also measuring coincidences of alpha particles, they were able to see and identify those events where the 2 neutrons, where helium-6 was not fused, but helium-6 transferred 2 neutrons over to the target, and the alpha particle came out. Okay, and they concluded, because of the nature of the Q value, etc., that there was no enhancement due to the fusion cross-section, and all one is seeing in this tail, which is in excess of the alpha particle, are really 2 neutron transfer events going across. Okay, so there's competing things going on. When you go neutron rich and very weakly bound, there's this additional new physics comes in, and I think that's sort of where we are at the moment. Okay, so there's some papers to read, and that's the conclusion. Okay, so talked about these barrier passing models. Hope you now know what they are. Hope you know what the characteristics are. Hope you have an idea how you go away and calculate them. Okay, and the boundary conditions, etc. And I've tried to stress with this sort of stuff over here the importance of collective excitations, the concept of the distribution of barriers, and how you can obtain that directly from the measurements, if the measurements are accurate enough to take derivatives of cross-section, and that these are an excellent way of identifying coupled channels effects And as I say, the role of breakup, etc., is still somewhat ambiguous and is ongoing. So more data will come when the beams get more intense and one can do low energy experiments for higher accuracy. Okay, so thanks for that. And I hope you'll try one of the examples. I don't think they'll take you very long, but please have a go at one so you can try and reproduce for yourself some of the stuff we've seen here. Okay, but that's after coffee. So thank you. Happy to answer questions, but I don't know if anybody has. I think you probably want coffee.